Today, we're going to continue on our journey of solving right triangles. We're just trying to get the mechanics down and make the process as simple as possible before we start doing applications of solving right triangles. Once we get that down, we can start solving other kinds of triangles. We start with right triangles to get the basic maneuvers down. So remember the solving right triangles, how the game works. Given 3, find 3. That's the solving right triangles game. In the right triangles version of the game, one of the 3 that you're given is a right angle. So the tools that we have in the toolbox are that the sum of the angles in a triangle is 180 degrees. That's for all triangles, not just right triangles. So we have a simplified version of the right triangle game. The 2 non-right angles in a right triangle are complementary. They'll add up to 90. Since we're using right triangles and we have a 90-degree angle, that means we have a hypotenuse, and that puts the Pythagorean theorem on the table. Since we have a right triangle, that puts trig functions as ratios on the table. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. What we are practicing now is how to use these trig ratios to solve for any one of those 3 variables in the trig ratio. Solve for the opposite, solve for the hypotenuse, solve for the angle. And we want to talk about the best practices and how to proceed when we're solving right triangles. The main thing that we want to remember is that the trig functions are there to connect angles and sides. The Pythagorean theorem is all about the sides. The sum of the angles is 180 degrees is all about the angles. The trig functions connect angles and sides. So that's why we need the trig function. It bridges the angle parts and the side parts. So I just picked sine of theta is opposite over hypotenuse and showed the 3 ways we could use it. Yesterday, we used it to solve for the opposite by taking the hypotenuse and multiplying by the sine of the angle. One thing that we didn't do yesterday is use this sine is opposite over hypotenuse and say that hypotenuse is opposite over sine of theta. But we did do the last one. We used the inverse trig function to find an angle. We got to remember to use inverse trig functions to solve for angles. One thing to notice here is that the sine of theta is opposite over hypotenuse. So this is just a statement in division. Sine is opposite over hypotenuse. That means opposite is hypotenuse times sine. That means hypotenuse is opposite divided by sine. The way to keep this straight is to remember that if we've got 3 times 2, that's equal to 6. Equivalent statements would be 2 is 6 divided by 3, and 3 is 6 divided by 2. Sometimes people remember this better in general. If A times B is equal to C, then B is C divided by A, and A is C divided by B. We got to remember what's being multiplied and what's being divided. This comes into play if I use this sine of theta is opposite over hypotenuse to solve for opposite. I do hypotenuse times sine of theta. But if I want the sine of theta to equal opposite over hypotenuse, if I want to use that to solve for the hypotenuse that's here in the denominator, I've got to do hypotenuse is opposite divided by sine of theta. All right. So we have gone over some things that we can mark as best practices when we're solving right triangles. One of them that I marked is that as soon as you have 2 angles, subtract to find the third. So Whatever you're being asked to solve for first, as soon as you have two angles, subtract to find the third. As soon as you know two angles, subtract to find the third. Clear out the minions before you focus on the boss. And it's really easy to subtract to find the third angle. So as soon as you know two angles, subtract to find the third. Number two, in best practices, there were two categories, and that we need to watch out for rounding error. And there are two entries for this. So B is going to be watch out for rounding error. And there are two entries in this. The best ways to watch out for rounding error, number one, if you have a choice, choose given information. If you have a choice, choose the given information, or information, because that's information that hasn't been rounded. So number one, if given the choice, choose given information or not rounded information. Use given or non-rounded information. If you have to use non-rounded information, use all the digits and only round at the very end. So if you must use rounded information, keep all the digits round at the end. Keep all the digits. You can use your calculator to help you keep track of all the digits so you don't have to write them down. So don't write them down. Don't write all the digits down, but keep them in your calculator. Don't write them down, keep them in your calculator. Right. So don't write them all down, but keep them in your calculator. So your calculator is not using rounded information. Either by using the answer key, if you happen to be using a TI-84, or by not rounding as you go. So these are the best practices that we have so far. As soon as you know two angles, subtract to find the third, because that's the easiest of all the operations. Some of the angles in a triangle is 180 degrees. That just involves subtraction. That's the easiest one to grab. Watch out for your rounding error. If you're given a choice, use given information because it hasn't been rounded, or use information that you know hasn't been rounded. All right, let's take a look at an example. Let's suppose a right triangle let's suppose the legs of a right triangle are, let's go with the 12.3 centimeters, and the other leg is 7.9 centimeters. I had to come up with another number and I got stumped. That's crazy. So here are three pieces of given information. Two legs of a right triangle are 12.3 and 7.9. And the right triangle part means one of the angles is 90 degrees. Since I called the 12.3 and the 7.9 legs of the right triangle, that means what we don't know is the hypotenuse. So if I'm going to draw a picture of this, I'm going to call one of these legs 12.3 and the other leg 7.9, which means we don't know what the hypotenuse is. If we knew the hypotenuse, I would have said one of the legs is 12.3 and the hypotenuse is whatever it is. At which point I wouldn't have needed to say right triangle. So in this case, we notice that we don't know what the any of the angles. So we're going to have to use inverse trig functions to find the angles. We're also going to notice that the 12.3 and the 7.9 have not been rounded. Here's the hard parts, or here's the good parts. We can solve for any one of the three pieces of missing information. Here's the hard parts. We can solve for any one of the three pieces of missing information, and we just have to choose. I want to finish labeling things. Normally, I've been labeling this vertical leg as B. And so if I label the vertical leg as B, that means this angle down here is going to be angle beta. And so that means this angle up here will be alpha, and 7.9 will be an A, because A should be opposite angle alpha, and B should be opposite angle beta, and C will be the hypotenuse, which we don't know. So, good news, we can solve for any one of those three things, alpha, beta, or the hypotenuse C. Bad news, we can solve for any one of those three things, alpha, beta, or the hypotenuse C, and we just have to choose. So, someone pick something that we're going to solve for. Just type it in the chat. All right, the poll seems to suggest C. The first response was alpha, which seems appropriate, but the majority of the responses have been C. So I'm going to go with the majority of the responses in C. Probably because that's the first thing that I would have done. What are we going to use to find C? We're given A and B. What can we use to find C? We'll use the Pythagorean theorem. First of all, this is a safe choice because finding C, we'll use A and B, and both of those pieces of information are given information. So I'm not using any rounded information when I use the Pythagorean theorem. So good news. Good news, everybody. I'm going to say A squared plus B squared equals C squared. We have to make sure that C squared is the hypotenuse. So A is a 7.9, so 7.9 squared plus B, which is 12.3. So 7.9 squared plus 12.3 squared is equal to c squared. So c is going to be the square roots of 7.9 squared plus 12.3 squared. I know I could have written the radical with the line going all the way over the sum instead of using parentheses, but I'm going to type it how my calculator is going to type it. And I want the square roots, so 7 square roots of 7.9 squared plus 12.3 squared, close parentheses, enter. 14.6. I'm going to round this to the nearest tenth. I'm just going to try to make it look like the other ones. All the sides are to the nearest tenth, so I'll just go with nearest tenth. We're not using some significant figures here yet, I guess. Since the two sides are in centimeters, I should label this 14.6 as being in centimeters as well. That will help remind us that it is a side. We're also going to notice that this has been rounded because we had 14.6184814.5. So I'm just going to make a note of that this is 14.6184814.5, and then we rounded to the nearest tenth. Now we have A and B and C. We have an abundance of information. We're going to go after alpha and beta. Beta never even came up in the suggestion, so I guess we're going to go after alpha first. So let's find alpha. Now, I have just sides. I need to use trig functions to find an angle. We know we're going to use inverse trig functions since we're looking for an angle. So let's remind ourselves, looking for an angle, we're going to use inverse trig functions. So we're going to use inverse trig functions. I don't know why everything's getting exclamation points. Well, actually, I do know it's because I'm shouting. The question is, why am I shouting? I think it's because I had an extra cup of coffee before class. So let's find angle alpha. What is side A relative to angle alpha? What is side A relative to angle alpha? Is it opposite, adjacent, or hypotenuse?
Opposite.
So A is opposite alpha. And what is 12.3 relative to alpha?
Adjacent.
So B is adjacent to alpha. So I have the given information is opposite alpha and adjacent to alpha. So what trig function am I going to use? Which trig function involves opposite and adjacent?
Tangent.
Tangent. So opposite and adjacent are given information. So opposite alpha and adjacent to alpha are given, so we'll use tangent. Once again, we're just following best practices. Use given information whenever possible to avoid rounding error. So I'm going to set up my trig ratio. The tangent of alpha will be opposite 7.9 divided by adjacent 12.3. Now we're going to use inverse trig functions to solve for alpha. So if tangent of alpha is 7.9 over 12.3, then alpha itself is the tangent inverse of 7.9 divided by 12.3. And I'm just going to write it in calculator syntax on a single line. So to get the inverse trig functions, I'm going to press second tangent to get the tangent inverse. And I'll do 7.9 divided by 12.3, close parentheses, and hit enter. And that is a 32.71167684 degree angle. I'm going to round to the nearest tenth. I can't remember what I asked you to round to on the quiz, so let's go with tenth for now. And we'll just make a note that this has been rounded. So if I want to use this 32.7, this is rounded information. So this is a 32.71167684 rounded to the nearest tenth. Oops. At this point, we have two angles, so we should subtract to find the third one. Here, this subtraction part is where we're going to be safe in just using the rounded angle. Because this is the last thing that we're going to find, we're going to be okay with this rounding. So as soon as we have two angles, the 90-degree angle and a 32.7, we subtract to find the third. We know two angles, so we subtract to find the third. In this case, the 32.7 has been rounded. So I want to avoid rounding error, so I'll say 90 minus whatever I had. I'm going to use the answer key because the calculator right now has a 32.71167684 button. So I'll do 90 minus the previous answer and hit enter. And now I'm not using rounded information. And I have 57 points rounded off to 3 degrees. Subtraction is the safest place to not worry so much about the rounding. So I'm just going to do beta is 90 minus alpha, which is 32.7. Notice that I'm not writing all these numbers. I'm just saying I'm subtracting 32.7. And I'm going to write that the answer is 57.3. This is what we get if we would have rounded this 57.28832.316. Subtraction would have been a safe place to do the rounding, because if I subtracted 32.7 from the 90, I'd have come up with 57.3 anyway. But we're trying to build best practices, and best practices work best when we understand why they work best. And so it works best if we know that the rounding in the subtraction part is going to work itself out. That's always going to be readily obvious that the rounding will work out.
I have a question.
Yes.
So when we were finding angle alpha,
Yes.
and we were using the inverse trigonometry,
Yes.
we decided it was tangent because opposite over adjacent.
Yes.
So it was 7.9 over 12.3. But when you use the inverse, don't you flip those around like it's one over the, like, isn't it
No.
backwards?
No, that's the inverse of multiplication. When we divide a fraction, we multiply by its reciprocal. But when we write tangent and then the -1, that's not 1 over tangent. That's tangent inverse,
Okay.
not an exponent of -1. That's a great question. And I'm glad it came up. So that was such a good question. People should be suspicious that that's an audience plant. So, but when we write tangent to the -1, it's not a -1 exponent. It's an abbreviation for inverse tangent. So tangent to the -1.
A little bit out. Can you scroll down?
Yeah. So tangent to the -1x is our notation for inverse tangent. It's not a -1 exponent. It's not a -1 exponent. So very important question. Thank you for that. The tangent to the -1 is our notation for the inverse tangent. So we don't read it as tangent to the -1. We read it as tangent inverse or inverse tangent, depending on what we see first. If we just go left to right, then we see tangent first, and we're like, oh, tangent. And then we see the -1 exponent. We're like, oh no, tangent inverse. If we see the whole thing at once, we'll say inverse tangent.
When I was
Go ahead.
sorry, when I was doing the 1.3, so like the one thing I got stuck on when it was getting to like inverse tangents, because like tangent inverse was like equal to like a whole nother word, like I don't know what it was, like cotangent, which was like, I think it's like,
Cotangent is the reciprocal of tangent.
yeah. So then I got into reciprocals, and that's where it got confusing because I thought that we had to do a reciprocal to find the angle.
Nope, we're not doing reciprocals to find angles. We're doing inverse trigonometric functions. So cotangent is the reciprocal of tangent. That's a multiplicative inverse, where tangent inverse is the inverse function.
So having that tangent inverse up there before the 7.9 over 12.3, it doesn't change anything in the actual math of it. Like when you do 7.9 divided by 12.
That's correct.
It's just there.
It's just we're saying inverse tangent of 7.9 over 12.3.
And 7.9 over 12.3 got us 32.7.
No, the tangent inverse of 7.9 over 12.3 got us to 32.7. 7.9 over 12.3 is 0.642. The
Okay.
tangent inverse of that number got us to the 32.7. So second tangent for tangent inverse of 0.642 to 7.64228. That's what got us to 32.7 degrees.
Oh, and that's the angle.
Yeah.
Okay. Thank you.
No problem. Any questions? Now, previously I said we could have solved for any one of these three missing pieces right at the beginning of the problem. Notice that when we calculated when we found alpha as tangent inverse of 7.9 over 12.3, that was using given information. We didn't use the piece of information that we found. We didn't use the 14.6. It's a little bit toxic. This has been rounded. I don't want to throw it into trig functions. Might get rounding error. And Leach is such a jerk. He'll take off points just because my answers are wrong. Oof, don't want that to happen. Notice that we could have used the tangent again with 12.3 and 7.9. 12.3 is adjacent to alpha, but it's opposite beta. 12.3 is opposite beta. And the 7.9 is adjacent to beta. So I could have done a tangent of beta equals 12.3 over 7.9. So I could have calculated beta as the tangent inverse of 12.3 divided by 7.9. And that would get me the 57.3 degree angle first. And then I could have just subtracted from 90 and found the 32.7 degree angle afterwards. We could have also used sine or cosine, but that would have involved the hypotenuse, because sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. And that would mean I'd have to use more digits than in my 14.6. Right now, we don't have a lot of experience doing that. So safe thing to do is to use the given information, use the stuff that we know isn't rounded. Any questions? So good news, everyone. We have options. Bad news, everyone. We have options. We always like to think that we want more options and that more options is better. But really what we want is few options, because then we'll be more confident in our choice. Any questions? Comments? Snide remarks? Like, imagine if there were only two vehicles that you could buy. You could either buy a sedan that seats 4 with 4 doors, or a truck that seats 3 but has a truck bed. Those are the only two cars in existence. Your choice is really easy. I need to transport children. I'm going to have to buy the sedan because I got more than one kid and I need to be able to seat 4. Or I'm going to have to haul stuff around. I need a thing with a bed. You buy the truck and you're fine with your choice. And you sit there and you wish you had more choices. But now, these days, if you want to buy a sedan, you buy the Toyota, the Honda, the Mazda, the Subaru, and it just list just keeps on going. And now you have to decide. Question? I see a hand raised.
Yeah, so I don't know what's happening, but whenever I plug in the same numbers, I'm not getting the 32.7 degrees. I'm getting a totally different number.
So you're doing this calculation. Are you coming up with 0.5709?
Yes.
Ah, see, I have magical powers. What you need to do is go into your mode and go in change from radian mode to degree mode.
Gotcha. How do I change modes?
So on your calculator, if you hit the mode button, if you have a TI-84,
There you go. Got it.
and then go down to degree and highlight it and then hit enter. Then if you run the calculation over again, just hit enter again, it'll give you the 32.7.
Okay, awesome.
Right. One of the things that we might run into is maybe we don't have a TI-84 because we're like, oh, I have a better calculator here because this one does better graphing than the TI-84. TI-84 is like, oh, I am a graphing calculator, and then the phone comes along and says, like, oh, I'm a better graphing calculator. Oh. But then the TI-84 comes back and says, well, I'm easy to use to actually make calculations. And then the iPhone is like, oh. So it's better to have both. Let's bring up the calculator I'm just going to use my iPhone calculator. So right now I'm going to get a text from one of my friends and it'll be embarrassing, but that's fine. So notice that our calculator in portrait mode is just going to be a normal 4-function calculator. But if we want it to be scientific, we have to switch to landscape mode. And that brings up our trig functions. So right down here, sine, cosine, and tangent. Now, one of the problems with this style of calculator is that it doesn't display. We can't just type things in as we see them. We can't just hit the buttons in the sequence of the thing that we're writing. This is why I like having the Texas Instruments calculator, because doing this calculation, I just type exactly what I see. The problem with the calculator on your phone, and it's probably the same on a Samsung phone. If you got that, I don't have a Samsung phone. I've got an iPhone. You can say, you can call me a cultist if you want. That's fine. I'm also have a MacBook Pro. So, and there are iPads all over the house. So if I want to do this calculation, I can't lead with the square root button, which is right here, the square root button. The square root button, the way that button works on your iPhone calculator or any calculator that just has a button layout like this, is it doesn't open up the command. It just takes the square root of whatever's on the screen. So if there's a 9 on the screen, it says it's 3. If there's a 15 on the screen, it says this it's 3.87. It just takes the square root of whatever's on the screen. So we have to do that last. I can do 7.9 squared, 7.9 squared to the second power, plus 12.3 squared, and then I have to equals, that's the sum of the 7.9 squared and the 12.3 squared, and I want the square root of that. Then I can hit the square root button to get my 14.6. So the calculator is not set up to type things the way that we write them, at least not with the square roots, the way we write square roots in front of our calculation. If we replace radicals with 1/2 exponents, then we can do things in order, but we still have to remember order of operations. So another thing to note is that I can do the tangent and tangent inverse button works the same way. So if I just try to hit the tangent inverse button, so I have to do the same thing. I have to press second and then tangent inverse. It just calculates the tangent inverse of whatever's on the screen. Oops. Oh, I didn't know it was a sticky button. So if I want to do the tangent inverse of 7.9 over 12.3, first I got to figure that out. I got to do 7.9 divided by 12.3 equals 0.642. You might remember this number from before. So this was a calculation that we did before. Oh, it's not there anymore. Oh, there it is. We did the 7.9 divided by 12.3. And then to do the tangent inverse of that, remember the tangent inverse button is only going to take the tangent inverse of whatever is on the screen at the moment. So we have to press second and then tangent inverse. And then instead of having to hit equals, it just does the tangent inverse of whatever's on the screen. So we got to be careful with, we have to know how our calculator works. We can't just plug things in like we type them. But both are perfectly effective at doing the calculation once we are used to how our calculators work and how the buttons behave. Like I said, I don't have a Samsung phone, so I'm not sure how the calculator is laid out. If it's laid out to be type what you see, then hit enter, or is it the buttons do the thing to whatever's on the screen? Yeah, type what you see, then hit enter is usually a little bit better because that's kind of how humans interface with machines now. We just type, like in Google, we just type what we want to look for. There's no codes or anything that we have to put in. We just. Who was that guy in that one movie that did the thing, you know, with that other guy? And then Google for somehow knows what we're talking about. And there's no somehow about it. They know because they're spying on us the whole time.
For algorithms.
Yes. The algorithm watches. Any questions about solving right triangles? At this point, we've done all the variations of things. The two big variations are, do I give you an angle and the right angle and one side, or is it right angle and two sides? Those are the ways I can set up a problem. I give you the right angle, an angle and a side, or the right angle and two sides. We just need to practice making the decisions following our best practices. Any questions, comments, or snide remarks?
I have a comment. I mean, I was trying to use the iPhone calculator
Yeah,
because I still haven't gotten my hands on the actual calculator. I went into Target and they had like the TI 84 plus, and it
right.
was like 120, and I was like, I don't want to drop 120 on it right now, you know.
Yeah,
So I held off to try to find one online now. But see, the struggle with that is I'm doing the homework now and having to use the internet to look up, like what's the tangent of this or what's the square root of this, because the iPhone calculator is so bad you can't even punch in like a specific number. Like I'm trying to put like tangent and then a number to get the tangent of that number, or that number divided by that number. It just doesn't let you put all those things in it.
yeah. So you just have to learn the syntax of the your phone's calculator, and the tangent buttons work differently. For what this goes back to the original calculators. They designed the button to just do the function of whatever's on the screen at that moment. So there's no hitting equal sign or anything like that.
So you're supposed to type this divided by this first and then click tangent.
Yes. So you'd have to do 7.9 divided by 12.3 equals, and then inverse tangent.
Okay.
You just have to get used to that. So
Yeah. I mean, it's definitely easier to just have one of the actual calculators.
yeah, this is a much better syntax. Syntax is what we have to type to interface with the machine. So the TI-84, I think, has the easiest syntax to work with.
Yeah, I don't mean to interrupt, but you can I'm pretty sure you can download like calculator apps, simulate like a graphic calculator phone.
I bet
Yeah, look
there's
interesting.
probably an
You
app.
can try that.
Yeah,
I was struggle with the default app.
you might find a free app while you're waiting. I'm sure there might be ads. So I saw a picture of an online calculator at one point. It said, pay $4.99 to unlock the plus operation. So. All right, so what we want to do this evening, everything's all blurry. This evening, I'm going to post your first quiz, and it will be solving a triangle. The first iteration of the quiz, I give you one of the angles and a side, and then ask you for the other three pieces of information. Once again, following best practice, as soon as you have two angles, you subtract to find the third angle. And so I emphasize that in the order I ask the questions on the quiz. So one of the things that I am quizzing you on is avoiding rounding error and rounding your answers correctly. So I put in zero tolerance, even though philosophically I disagree with zero tolerance policies. When the point is that you round things properly, it's not unreasonable to say round to the nearest tenth, and it has to say on this one 14.6. Any questions? Comments? Snide remarks? There are plenty of students and teachers out there that are like, well, that's unreasonable. You should give them a tolerance. And then Wiley Plus has tolerances of like 2%. And I got 2% tolerance means they have to be an exact in almost every situation I've ever seen it. The quiz will be due along with the homework on the 30th, if that's the day that I picked. But if you miss the due date, the quiz will still be available after the due date. That's just when I agree that I'm going to start grading it. So on Tuesday, the quiz is due. Next day, I just start grading the quiz so you can see what your results are. Then you can continue working on the quiz. So if you get one of the problems wrong, you can just do the quiz over again. And you can submit the quiz as many times as you need to until you get it right, because that's how we learn things. We practice it. We don't just do things once and have someone say, that was bad. You do it over and over again until you get it right. Any questions? I know that this process works because I've had students in other classes submit quizzes like 5 or 6 times. That is the correct result. That's what I want to happen. They're like, oh, I keep getting this wrong. What's wrong? And they keep making adjustments and then they get it right. So they've learned something rather than just submitting it once, getting marked down, and then being made to feel bad. That's the worst part. When students are made to feel bad about getting things wrong. Getting things wrong should be celebrated. Like, oh, I got this wrong. That's awesome. I have to work and learn something now. You know what I mean? Imagine if your guitar teacher taught you like a math teacher. You played that song incorrect. You flunk, get out. Well, that's not how that works. Why does math think it has to work that way? You play it wrong on guitar, you're like, oh, that's not how it works. Try it again. Try it again. Try it again. I mean, you just keep doing it until it works. You know what I mean? So I mean, the argument against unlimited attempts is like, oh, they're going to keep trying until they just get the right answer. I'm like, well, yeah, that's what they're supposed to do. You know what I mean? All right. That's going to do it for today. I want you to get in and continue doing the homework on chapter 1, where we're solving some triangles and doing some other stuff that's kind of around solving triangles. Some of the homework is kind of like near solving triangles, in the neighborhood of solving right triangles, but that's kind of the big thing that we're working on. If you come across a word problem and you're like, oh, I don't like word problems. I'm like, oh, first of all, that's a bad idea. Word problems have to make sense. If it's like, oh, how long should the runway be? And you're like 15 feet, that's too short for a runway for a plane that's already 300 feet long. So maybe go back to the drawing board on that one. You know what I mean? So word problems are better because the answers need to make kind of sense. But all the word problems that you're going to come across in this chapter, there's a right triangle in there somewhere, and all you got to do is solve that triangle. All right, that's going to do it for today. That's going to do it for this week. I'll see y'all on Tuesday. Everybody have a good weekend, and thanks for playing.